Welcome to Population Health, Big Data, Interoperability, and Analytics for Population Health. This is Lecture B. This component, Population Health, discusses the application of informatics and informatics methods in population health management. This unit, Big Data, Interoperability, and Analytics for Population Health, explains the challenges and opportunities of developing predictive analytics for population health. The objectives for this lecture are to describe the conceptual and practical challenges of developing valid and reliable population health analytic methods, explain how population health analytic models are evaluated and compared against each other, explain the challenges and opportunities of population health analytics in special populations such as pediatric, mental health, and long-term care populations. Note that this unit does not explain the details of predictive modeling techniques. Please refer to the dedicated component on data analytics to learn more about predictive modeling and analytics in general. This lecture discusses the common modeling challenges faced by population health analysts. This diagram shows the overall steps involved in developing analytics for population health management and risk stratification. As shown in Box 1, the first stage involves the merging of various datasets and developing a centralized or distributed population health data warehouse. The second step, depicted by Box 2, includes various processes to prepare the data for analysis, such as fixing data quality issues, deleting or imputing the missing data, and transforming the data to meet the assumptions of a given analytical approach. The next step contains the development of the modeling and data mining approaches. As depicted in Box 3, this step usually requires a base dataset and an outcome dataset that would collectively include the dependent and independent variables. As illustrated in Box 4, the next step contains the model's validation and evaluation process. In this phase, the analysts use various statistical and data mining concepts to measure how good the model is in differentiating the outcome variable and how reproducible it is when used on other datasets. As pictured in Boxes 5 and 6, a critical step after an acceptable model is developed is to apply it within the context of a population health management workflow. As marked by Circle B, this lecture discusses the issues with preparing population health data and model evaluation. Other phases of the population health analytic process are discussed in other lectures. This lecture reviews the common challenges faced by analysts to develop predictive models for population health management. These challenges include, but are not limited to, issues with data preparation, such as data selection, data processing, data transformation, and feature reduction. Limitations with population health predictive modeling, such as assumptions, mechanics, and outputs. Complexities with selecting the most useful model among a series of population health models, including evaluating and choosing the right model by using various methods, such as goodness of fit and reproducibility scores. And finally, challenges of developing predictive models in special populations, such as pediatric, mental health, disabled, or long-term care denominators. Data preparation is probably the most time-consuming step in the entire process of population health data analysis. Data preparation involves data selection, which includes selecting appropriate data sources based on the population health goals of the model and also having prior knowledge of their effect on the measured outcome. Data processing, which involves cleaning the data by minimizing potential noise and removing outliers, and also applying strategies to handle missing data. Paying attention to the time sequence information and assuring the validity of the timestamps are also critical. Data transformation, which entails transforming the data to fit with the model's assumption, such as log transformation to make cost data normally distributed and hence suitable to be fed into certain types of models that have such prerequisites. Data reduction, which means finding useful features, independent variables, to represent the data and applying dimensionality reduction functions. In other words, this process reduces the number of variables that will end up in a model. This diagram shows the challenges that population health analysts often face when preparing the data for analysis. The left side of the diagram shows the first steps of the routine population health data analysis process, which is extensively discussed in the previous lecture. The right side of the diagram shows examples of the actions that analysts take to remedy data preparation problems. Data preparation usually involves checking and amending the quality of the data, treating the missing data appropriately, and transforming the data to match a certain format, scale, or distribution required by a model. Data preprocessing or cleaning may include imputing missing values, truncating outliers, normalizing the noise, adjusting errors or biases, correcting typos, and many other techniques to improve the quality of the data. Data transformation includes mathematical functions that can help to fit the data into desired distributions. For example, cost is often highly skewed, and a log action can help make its distribution more normal. Finally, data reduction techniques will enable analysts to reduce the dimension of the features by creating a derived variable representing a number of variables, dropping variables that are highly correlated with others or are statistically not significant, or removing them simply because it does not make sense to keep them in the model. Data preparation is usually a combined manual and automated process. A predictive model is an abstraction of the real world. A good model attempts to capture the most important features of the complex health interactions in simple mathematical or statistical terms. However, a model is never completely representative of a given situation. Indeed, a model should be able to capture the main relationships and predict behaviors in a variety of situations and environments. But it is not required to be always correct in predicting the exact outcomes. In population health, a model is often a set of coefficients that can be applied within a data environment to generate a prediction of some outcome. For example, if the population health model is defined using a regression method, the model will be presented as an equation, where the right side of it represents all of the predictors, also known as independent variables, and the left side represents the predicted outcome, also known as the dependent variable. As shown in the figure, a regression model includes various components, including y-hat, or the dependent variable. Y-hat is called the dependent variable because its value always depends on the values assigned to the variables on the other side of the equation. In population health, y-hat is usually referred to as the predicted outcome, such as predicted cost. Note that regression models always try to keep the predicted outcome, y-hat, close to the actual outcome. The actual outcome variable, or y without the hat, is not included in this model. X's or independent variables. X's are called the independent variables because their values, hypothetically, do not change if other variables in the equation change. In population health, these independent variables are often the typical predictors, such as age, sex, diagnosis, medication, and other data types. Intercept or the first beta. The intercept shows the unexplained constant of the outcome. If the intercept comprises most of the y-hat, then the model is not easily predicting much of the y-hat's variation. Other betas and coefficients. Coefficients show the magnitude with which each of the independent variables affects the outcome. There are usually a series of assumptions about the nature of the data and its types, variance, distribution, and quality when using certain statistical methods. The common predictive modeling techniques that are used in population health often have restricting assumptions about the underlying data. For example, regression models assume there is a linear relationship between variables. There is an independence of errors. A normality of the error distribution and multivariate normality exist, which is basically the fact that whatever that could not be predicted is not following a special pattern. Errors are homoscedasticity and have a constant variance. and there is no or little multicollinearity or correlation between independent variables. Of course, other statistical methods may have other assumptions. Note that the typical variations in population health data often do not follow all of the assumptions of a given statistical method. Thus, population health data must often go through some sort of manipulation before it is used in the modeling process. These diagrams show the various assumptions needed to develop a linear regression model. As depicted on the left side of the diagram, an ideal scatter plot of a given outcome and one predictor should follow a linear format. Any of the distributions depicted in the scatter plots on the right side may violate the assumptions of the linear regression models. These potential violations could be caused by the following relationships: nonlinearity of the data, dependence of errors, heteroscedasticity of the data, and non-normal errors. Note that these distributions often do occur in population health analytics, and analysts should be aware of potential threats to their models. There should be minimal multicollinearity of independent variables if linear regression is used for population health modeling. For example, if a population health model is using two x's, x1 and x2, to predict y, then these x's should not be highly correlated, especially when predicting y. As depicted on the left side, if the two x's do not have multicollinearity, then the model will perform stably, however. If the model has partial or high multicollinearity among its independent variables, as shown on the right side, then the model will face issues. In population health analytics, a base dataset and an outcome dataset are usually used to develop a predictive model. Often, the base dataset is a time period, base year, before the outcome dataset, future year. The models produced through this model are often called predictive. Sometimes base and outcome datasets are extracted from the same time frame. These models are sometimes referred to as concurrent models, as they are predicting the same time frame. Note that these models are still predictive, however. The main reason for setting aside an entire year of data for the base and another year for the outcome is due to the common use of claims data for population health modeling. As other data sources are becoming more mainstream in developing population health models, the use of different time frames, such as 1 month, 3 months, and 6 months, are also becoming acceptable. This diagram shows the two common methods of extracting information for population health models. In predictive models, as shown in Circle 1, the base dataset, which is usually 1 year of claims data, is used to provide all of the independent variables for the model. However, the outcome dataset, which is next year's claims, provides the outcome, such as cost. In concurrent models, indicated by Circle 2, the base year provides both the base and the outcome datasets. Usually, concurrent models have a higher accuracy, as using the same year's outcome, such as cost, is less variable than using next year's outcome. If using the linear regression methodology, the equation discussed in previous slides can be translated as predicted cost is a linear function of age, sex, diagnosis, and medications. Note that the actual population health predictive models are usually very complex, as categorical variables, such as diagnoses, cannot be represented as single variables, and indeed may introduce hundreds of diagnostic codes. While using certain methods, such as linear regression, if no specific data transformation has occurred, the predictive model can be used to generate a predicted outcome, such as cost for a given patient. These predicted values can then be used to compare the model's accuracy. For example, if the developed model is linear, as shown in this figure, we can use the model to predict the cost outcome for 3 sample patients. The model shows that the predicted cost is equal to minus 18.5 units plus 358.1 multiplied by the drug counts of a patient, plus 414.5 multiplied by the drug class counts, plus 0.5 of prior cost, plus 1,818.9 of diabetes presence, plus 57.5 multiplied by diagnoses count. On the far right side, the figure shows how each of the coefficients of the model are used to calculate the cost for patient number 3. This patient does not have any diagnosis and is not taking any drugs, but has had a prior cost from base year of $2,000. Thus, the total predicted cost of this patient is minus 18.5 plus 0.5 multiplied by the patient's prior cost, which is $2,000. Therefore, the total cost for patient number 3 is calculated by the model to be $981.50. Calculation steps for patient number 1 and number 2 are not shown in this figure, but the total predicted cost can be found for each of them. Now, if the actual cost of all of these patients is available, you can compare the predicted cost with the actual cost and evaluate how well the model is performing. For example, for patient number 3, the predicted cost of $981.50 is lower than the actual cost of $1,053. Population health models need to be evaluated frequently to ensure high power and accuracy. Overall, quality measures of a population health risk model can be defined by various measures. A model needs to be parsimonious. This means that a model should introduce as few variables as necessary to capture the main essence of the phenomenon under study, and leave the minor variation to the error. For example, if a model is trying to predict cost for a given population, it is preferred to have the shortest list of independent variables that can explain the highest amount of variation in that cost. A model should have an acceptable level of fit. Indeed, a population health model should explain the differences in the outcome variable, such as cost, hospitalization, or ER admission, to a high degree by the explanatory variables. A model should contain theoretical consistency, and the relationships expressed by the model should be theoretically plausible. This means if X is used in a model to predict Y, then the positive and negative coefficient of X should match with the actual relationship of these two variables in the real world. For example, a population health model that has a negative coefficient for age to predict cost will require some explanation. A model should have predictive power and be reproducible. Its effectiveness is in its predictive accuracy when applied to different data and time periods. Population health analysts often employ different evaluation techniques to examine the reproducibility of the models, such as cross-validation and bootstrapping. Different statistical methods are evaluated by different approaches. In the case of regression models, their goodness of fit can be evaluated by various statistical scores, such as R-squared, F-test, C-stat, and others. Adjusted R-square explains the proportion of the total variation that can be explained by its regression on the associated independent variables. R-squared ranges between 0 and 1, and in general, the higher the R-square number, the better the mode fits your data. R-square, however, cannot determine whether the coefficient estimates and predictions are biased. Linear regression, which predicts a continuous variable, such as cost, usually produces R-square as one of its evaluation scores. F-test provides the ratio of variance explained by the model divided by unexplained or error variance of the model. C-stat, or the area under the curve, AUC, of a receiver operating characteristics, ROC curve, provides a performance measure for models that predict a binary outcome. For example, logistic regression is a binomial model in which a two-state condition is predicted, such as being in the top 5% of spenders versus not being in that group. C-stat varies between 0.5 and 1. The highest C-stat generally indicates a better performing model. There are also other advanced methods to measure the accuracy and performance of predictive models. However, they are out of the scope of this lecture. In order to measure how well a model will perform elsewhere, the generalizability or reproducibility of the model should be measured. This is different from how well a model predicts the outcome within the same dataset that is used to train the model. In these cases, a testing dataset is usually used to evaluate the reproducibility of the model. If a regression model was used, the following methods can help evaluate its generalizability. Jackknife method, which systematically leaves out each observation from a dataset, calculates the estimate and then finds the averages of these calculations. Bootstrapping, which is a method that relies on random sampling with replacement from an original sample. And cross-validation, which is a technique for assessing how the results of a statistical analysis will generalize to an independent dataset. The main reason that evaluating reproducibility is crucial is the fact that overfitting may occur while a model is overtrained. Indeed, overtraining not only predicts the main relationships between independent variables and the dependent variable, but also the noise of the data. To understand the issue with model evaluation better, the distribution of the model's predictions can be compared to the actual value of the total population. This figure shows two normal distributions of true positive and true negative populations for a given outcome, such as being a high utilizer or not. As depicted in this figure, if a model can differentiate two populations perfectly, then the model does not produce any false positives or false negatives. For example, let's assume hypothetically that a population health model uses a diagnostic code to differentiate the top 5% of utilizers from the bottom 95% of utilizers. As shown, this model makes a correct differentiation between these two groups 100% of the time and only generates true positives and true negatives. However, it should be noted that such explicit differentiations are almost impossible to find, as the embedded distribution of errors and the natural variance of typical population health outcomes always overlap between the positive and negative outcomes. As discussed in the last diagram, the natural variance of typical population health outcomes always overlaps between the positive and negative outcomes. This diagram shows the overlap of two normal distributions of true positive and true negative populations for a given outcome, such as cost. In this condition, the population health model cannot make a clear split between the top utilizers and the bottom or non-top utilizers. The overlap of the two normal distributions forces the model to make compromises where the two diagrams overlap. As depicted in the diagram, this leads to the creation of false negative and false positive cases, in which the model either misses the correct attribution of a denominator of patients to top utilizers or assigns them to the bottom utilizers by mistake. Of course, if this overlap is larger, the share of false positives and false negatives will increase, while the share of true positives and true negatives will decrease. And if the model's criteria, the dotted line, is moved to the left or right, the proportion of all components will change. More specifically, the false positive, false negative, true positive, and true negative rates of a model can be summarized into terms more easily communicated and understood. This chart shows how the combination of these ratios constructs such concepts as sensitivity and specificity. As depicted, sensitivity is the true positive rate divided by the total sum of true positives and false negatives, while specificity is the true negative rate divided by the total sum of true negatives and false positives. In other words, sensitivity is concerned with minimizing false negatives, which are missed true cases, and is trying to make the model more inclusive of positives. Specificity is concerned with minimizing false positives, which are wrongly marked cases, and is trying to make the model more exclusive of negatives. Of course, due to the overlap of the distributions between the positive and negative populations, sensitivity and specificity can never reach the ideal value of 100%, as moving the model's discriminatory target to the right or left only shifts the percentages between these two. The previous slide showed the calculation of sensitivity and specificity for a given model to distinguish a negative outcome from a positive outcome, such as being in the top 5% of spenders in a population versus not being in that group. Previous slides also showed that an arbitrary threshold can be used to consider a case in either the top 5% of spenders or not, which was depicted by a dotted line in the normal distribution curves. This dotted line can be moved to the left or the right side of the curve to represent various thresholds and thus change the membership of individuals in the top 5% spender group. Indeed, when moving the dotted line to each side, the analyst is changing the threshold for the assignment of a given patient to each of the two groups, top 5% of spenders and the non-top spenders. Note that methods like logistic regression predict the likelihood of a patient belonging to one of the spending groups, thus creating a continuous number between 0 and 1 that represents the odds ratio. And of course, it's up to the analyst to define at which point the patients should be assigned to either the top spending or non-top spending groups. Now, if this threshold is moved from 0 to 1, as depicted in the left diagrams by the dotted lines, a different sensitivity and specificity can be calculated at each threshold, as the underlying false negative and false positive rates are going to change. These moving sensitivities and specificities rates can be plotted against each other to see how the model performs throughout the range of thresholds that assigns patients to either the two outcomes, such as high-risk and non-high-risk populations. These plots are called the receiver operating characteristic or ROC curves, as shown on the right side of the slide. The interesting part is that multiple models can be plotted the same way to compare them against each other. Naturally, the models with higher rates of sensitivity and specificity are preferred to the others. This means that moving away from the diagonal line of the ROC curve, which represents random chance, is desired by the analysts. Note that the area under the curve, or AUC, provides a numeric measure for this preferred movement of the performance curve from center of the ROC curve to the highest combined sensitivity and specificity rates. AUC varies between 0.5, representing random chance, and 1, which is an ideal model with no false negatives and no false positives. Selecting the most useful model, especially in the other models in which the outcome is not simply binary, is even more complex. For example, the Akaike Information Criterion, or AIC, represents a complex measure of the relative quality of statistical models for a given set of data. Indeed, given a collection of models for the same population health data, AIC estimates the quality of each model relative to the other models. However, AIC does not reveal the quality of the model in an absolute sense, and even if all the candidate models fit poorly, AIC will not give any warning. Modeling for special populations requires expertise and extra attention to potential pitfalls. In the pediatric population, the following issues may affect the development of predictive models. The pediatric population generally has a lower rate of chronic conditions and relatively lower mortality and morbidity rates. Plus, this population often has lower healthcare expenditures than adults. Certain independent variables, such as growth and development milestones, functional status, family support, and social environment, are critical in defining different risk groups in the pediatric population. Pediatric population health is affected by school-based healthcare systems and other public health services that do not show up in claims, and bring other coding issues while developing population health data warehouses. Generally, most predictive models produce lower explained variance for the pediatric population than adults. Another special population that requires extra attention when developing predictive models is the population with mental health problems. In the mental health population, the following issues may affect the development of predictive models. Most models developed for this population are local and limited in scope and are often highly specific to the developer's goals. Models usually use diagnostic codes. However, these codes are not always accurately captured for mental health conditions and disorders. The underlying data and the models often do not represent or measure the severity of mental health issues. Utilization rates for mental health problems vary among providers due to the variations in the process of care. Most models produce lower explained variance for the mental health population than other populations. The population with disabilities also requires extra attention when developing predictive models. In the disabled population, the following issues may affect the development of predictive models. Disability has different definitions depending on the source and use case. Thus, models often are not well calibrated to predict the same outcome. Disability is caused by various factors, ranging from congenital to environmental factors, many of which are not available in common population health data sources. People with disabling conditions are not necessarily sick. Thus, defining disability as risk is not always straightforward. Prior functional levels are the best predictors of future disability levels, such as the use of active daily living or ADL surveys. However, such survey information is limited across a large population data warehouse. Insurance claims data include useful information that can be used to identify disability, such as diagnosis, procedures, and extra information on durable medical equipment, but none of them are reliable. And finally, the development of predictive models is also complex for a population denominator that requires long-term care. In the long-term care population, the following issues may affect the development of predictive models. There is a growing demand for long-term care and an obvious need for risk-based adjustment. However, risk-based adjusted reimbursements have not been widely applied to this population yet. There are more emerging databases with details of long-term care at the clinical level. However, analysts often have a hard time acquiring large-scale population-wide data warehouses for long-term care patients. There is an increasing number of predictive models developed for long-term care. While their accuracy to predict utilization in the long-term care population has increased over time, their accuracy is still behind predictive models developed for other population denominators. Patient satisfaction and preferences are important in predicting risk in the long-term care population. However, this information is often missing in existing population health data warehouses. This lack of patient-centered data makes the development of predictive models even harder for the long-term care population. This concludes Lecture B of Big Data, Interoperability, and Analytics for Population Health. This lecture discussed data preparation issues such as selecting, preprocessing, transforming, and reducing the dimension of population health datasets. Population health modeling issues such as identifying appropriate models, conforming to the assumptions, knowing the mechanics, and understanding the outputs. Choosing the right model by measuring the overall quality of a model, including its goodness of fit and reproducibility, as well as selecting the most useful model. And finally, the challenges of modeling in special populations, such as the pediatric population and populations with mental health, disability, or long-term care issues.